Today's advanced study will be discussing molecular geometry, the Vesper Theory, valence shell electron pair repulsion theory. Some of the tool pages I have ready for our lesson. I have the periodic table, simply because we'll need to be able to look up how many valence electrons we have for each element involved in the compound that we're drawing. I've also printed the Vesper Theory molecular shape test-taking tool page. What it helps me to do is to predict the molecular geometry, the bond angles, the hybridization, and so forth by simply looking up the characteristics we find after drawing a rough draft of our molecule. It's 2 pages. Yours might be front and back. Mine are 2 separate pages. We've also printed a copy of the advanced study, the models of molecules, and there'll be 5 involved for our advanced study project. Remember that we are altering what's in the book by adding this on. So this is something that you had to print along with the data sheets. The data sheets are simply a repetitive page over and over of a table that includes all of the things we'll be asked to do for each of these 5 compounds. The reason I wanted to do these 5 compounds with you to get you an idea of what the actual data table will look like as we begin in lab building those compounds. There'll be 20 of those. So this is something else that you've actually printed from your Blackboard site. The models of molecules, all 20 of those compounds will be built during our laboratory session together. Notice also that that had plenty of data table pages, so you have enough of those data table pages forever. How large you write. It's all different for each one of us. Alrighty, so let's get organized and begin. The objective of our advanced study is to predict the shapes of molecules using the Vesper theory, the valence shell electron pair repulsion theory. The shape of the molecule we know greatly affects its property, and so in our activity we're going to use molecular model kits to determine the shapes of the small molecules represented by those compounds below. In the lab, we will do for 20 structures. In the advanced study, we are going to do 5 together just to get the hang of what it is we're being asked to do during lab time. When you arrive to lab, you'll be given one of these model kits. And in the model kit, you'll have different colors representing different elements. And what you'll have are plenty of hydrogens. The black ones represent carbons. Here you have oxygen. You have halogens, such as chlorine, fluorine, iodine. You have phosphorus, whatever it is the element is. You're going to notice that each one of them have just a different number of holes drilled into them, already pre-assembled correctly for electron geometry, helping us predict bond angles. So there'll be some balls that have 2 holes drilled, some that have 3, some that have 4, some that have 5, and even some that have 6 holes, depending upon the correct domain that we'll be drawing for. So the first essential step is when you're building, make sure that you grab the central atom that corresponds to the number of electron domains that we need. And I've tried to take a selection of each of those domains so we can visit each part of the Vesper theory. The valence shell electron pair repulsion theory, the Vesper theory. I had a moment of dyslexia there, it looks like. So we're going to draw for carbon dioxide, aluminum bromide, phosphine, which is pH 3, arsenic pentafluoride, and selenium hexachloride. 5 molecular compounds that are covalently bonded, and we'll get an idea of what to do. So the first compound we're going to draw for is carbon dioxide. So the first thing I'll do is just transfer. Number 1, CO2 is going to be the first structure that we draw. So number 1, CO2. And as we begin, probably the best idea is to just have plenty of scrap paper so we get an idea of what it is we're working with. Alrighty, so I have some scrap paper, and we're going to just kind of get together with some CO2 before we go to our permanent lab report. First thing that we're asked to do is to identify how many electrons that we have to bond with. So count the number of electrons available for bonding. Step 1. And all that means is with the help of our periodic table, carbon, who lives in group 4, will have 4 electrons. Oxygen, who lives in group 6, will have 6 electrons, and so we're counting the total number of dots. Carbon has 4, oxygen has 6, but we see 2 of them for a total of 12. By the time we're done, we have to place 16 dots, or 16 electrons, no more, no less. That's what we're allowed. Step number 2, place the least electronegative element in the central atom position. Place the least electronegative element in the central atom position. Sorry, I was speaking and trying to write. Central atom position. In other words, who's the element farthest from fluorine is the least electronegative. Between carbon and oxygen, carbon is the farthest from fluorine. It's the least electronegative. And also I want you to consider symmetry. When molecules build themselves, they do so by using this beautiful symmetrical part of nature where we take that central atom and attach everything back to it. The central atom typically is the one you have just one of, and for us it will be carbon. Alrighty, so carbon goes in the center atom position. So central atom equal carbon. The third position says, the third step here says, attach all other elements back to the central atom using a single bond. Attach the other atoms back to the center using single bonds. All right. Step 1, we counted the dots. Step 2, we placed the central atom, the least electronegative, which is carbon, and now we're going to attach back to the central atom using single bonds, and I want you to tally up what we've used already for our particular bonding. Remember, each single bond represents 2 electrons. We had 16 to start with. We just used up 1, 2, 3, 4, giving us 12 remaining. Tally what's left after we attach the central bonds. Step 4, when we're drawing Lewis dot configuration, says fill the octet of the outer atoms. The outer atoms, not the central, but the outer atoms are oxygen. 1, 2, 3, 4, 5, 6, filling that octet. 7, 8 right there. 9, 10, 11, 12, 13, 14. 2, 4, 6, 8, 10, 12. I counted wrong, sorry. So I placed the octets. We had 12 remaining. I just used 12 dots. I have none left. Clearly, we need to examine the structure. Does everyone have a full outer octet? Do all atoms have a full octet? And here we examine, we say no, this carbon only has 4 electrons assigned to it. It also needs to have 8. If they were all even, if they all had 8, we'd be done. But here we have an answer that says no, clearly we don't. So now I know that multiple bonds are involved. A double, or perhaps a single, or a triple. Multiple bonds, or double or triple bonds. And if I used up all my electrons, which I have, and not everybody has an octet, now I know that double bonds are involved. Think symmetry as well. The 2 electrons that are on the top, doesn't matter which set I grab, they're all created equal. They're going to need to be placed in the center so that carbon can share. Think symmetry. It wouldn't make sense to have triple bond one way and a single bond the other way, just thinking about formal charge and so forth. Here is the same thing going to happen here. One set of electrons goes in between them so that now the carbon can have 8 electrons. And if I simply redraw, we end up with carbon in the center, double bond in each direction to the oxygen. Now when I count 2, 4, 6, 8 on the oxygen, 2, 4, 6, 8 on the carbon, 2, 4, 6, 8 on this oxygen, we have satisfied the octet. Discussing formal charge is important here as well. The group number that it lives in minus the assigned electrons is how I assign formal charge. The group number minus the assigned electrons. Typically what you see as a little trick is to take the electrons that you're counting, from around a certain atom and draw a circle around it. Each electron is represented by a dot, and half of the electrons in a shared pair are assigned in either direction. So if I think about oxygen's formal charge, oxygen lives in group 6. It is assigned 1, 2, 3, 4, 5, 6 electrons. It has a formal charge of 0. That's what we want, isn't it? Carbon, who lives in group 4A, you see carbon right here, group 4A, has, again, draw a little circle around it if that helps, 1, 2, 3, 4 electrons assigned to it, lives in group 4. It has a formal charge of 0. That's what we want. And this oxygen is parallel to the other, so assigned group 6, 6 electrons assigned to it, formal charge of 0. If we had created a scenario where we had a triple bond in one direction and a single bond in the other, let's examine that, why it's not the best choice based on formal charge. If I redraw the compound and I had selected a triple bond, single bond, this is what would have happened related to formal charge. Again, just kind of draw a circle around the oxygen that you're counting. The group number oxygen lives in is group 6. It is assigned 1, 2, 3, 4, 5 electrons. It has a formal charge of +1. Not ideal. The carbon, 1, 2, 3, 4, lives in group 4, assigned 4. Its formal charge is 0. That's still fine. But over here now, when I consider the other oxygen, draw a circle around it. Oops, dissecting the bond. 1, 2, 3, 4, 5, 6, 7 still lives in group 6, but 7 electrons are assigned to it. This oxygen has a formal charge of -1. Formal charge -1, formal charge of +1 is not the best structure when I can draw it differently with all formal charges of 0. So we consider formal charge when we have options of how to go about distributing multiple bonds. We want to alleviate any formal charge if possible. By creating 2 double bonds, one in either direction, all formal charges are 0. If we had gone triple, single, we develop formal charges, which is not the ideal situation. So after all of that, we've decided that this indeed is our best structure. See why I have lots of scrap paper before I commit to my data table. For the carbon dioxide, we've just decided on the best picture. I'm going to draw carbon dioxide in a linear format and just put C double bond O in either direction. Now let's illustrate how I knew that was a linear direction. We have, well, I can even show this. I created a carbon dioxide molecule from our ball and stick model here. All right, carbon in the center. See how I've got double bonds by using 2 of those structures that allow us to connect elements together. So these bonding sticks here. By placing 2 of them, you can see now how I've created a double bond. In the center, there's 1, 2 electron domains. If I'm looking at the central atom carbon, I look left and I look right. That's it. There's only 2 domains to look at, and both of them happen to be bonded. If I have 2 bonded atoms, and on the central atom there are no lone pairs, I know that the molecule is linear. The electron domain is also linear. An example is carbon dioxide. The hybridization and the bond angles are listed here as well. See how nice this particular chart is in showing us not necessarily something to memorize, but the central atom for hybridization has 2 attachments. Remember, your thumb is always the S configuration, and I have just 1 more to go, so it goes SP. The hybridization of 2 domains is SP. So here we have all of those answers just listed right here for us that we just need to transfer onto our particular sheet. The number of domains from the central atom, there are 2. There's something to the left and something to the right. Remember that domains, it doesn't matter if it's a single, double, or a triple bond, that's 1 electron domain. Out of those 2 domains, both are bonded and 0 are non-bonded. There are known electron pairs. So non-bonding domains is another way of saying electrons that are unbonded. Unbonded electron pairs. There are none in carbon dioxide. So we know that the geometry is linear. The electron domain is also linear. This molecule is perfectly symmetrical, so it is non-polar. The bond angle of a straight line is 180 degrees, and its hybridization is sp. I am asked to draw the correct bond angles, so from the oxygen to oxygen is 180 degrees. That's our first of the 5 molecules. In the second example for our pre-lab, we are being asked to draw a compound of aluminum bromide, AlBr3. AlBr3, so I'm just going to write compound 2, AlBr3. This looks like aluminum with 3 valence electrons, and each of the chlorine has 7 valence electrons. Let's tally how many total dots we get to use. Alrighty, so again, just scrap paper until you get really good at this. I highly recommend scrap paper. AlBr3. We said aluminum has 3 valence electrons. Bromine has 7 valence electrons, and there's 3 of them in the compound for a total of 21 dots. The sum of the number of dots we get to use is 24. So step 1, count the number of electrons you have to use when creating your structure. That comes from the group number that they live in. 24 electrons, step number 1. Step 2 says find the least electronegative element and place it in the center. The least electronegative element is the one farthest from fluorine. Here's fluorine, there's aluminum. Bromine and aluminum also consider symmetry. Always select the element you have just one of and attach back to it. Aluminum is the least electronegative element. It will be the central atom, and the 3 bromines will attach back. So we selected the central element, step 2. Step 3, attach those elements, those other atoms, back to the central atom with single bonds. We have 3 bromines to attach back to the central atom. How many electrons did we use with single bonds? We used 2, 4, 6. So that gives us a total of 18 electrons left. Step 4 says fill the octets of all of the elements except the central atom. Fill the outer elements first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have no electrons left. Step 5, do we obey the octet rule? Consider formal charges. I'm going to just write that as FC. Consider the formal charge when deciding if we need a double bond. And here's what we're saying. Remember how aluminum lives in group 3? It's assigned 3 electrons. The formal charge right now on aluminum, its group number is 3. Assigned electrons is 3. Its formal charge is 0. Bromines, every one of them's the same. The group number is 7. It lives in group 7. We also are assigning it 7 electrons, 2, 4, 6, and half of the bonded pair. is also 7, so the assigned electrons is 7. Each one of those has a formal charge of 0. If I were to consider a double bond to fill the aluminum octet, we will continue our molecular geometry. We were drawing pH3. We said phosphorus, who lives in group 5A, would have 5 valence electrons, and each of the hydrogen has 1. There's 3 of them, so we have a total of 8 hydrogens. We also mentioned that we should never select hydrogen to be in the center. It's always attached back to the central atom or even further out yet. That means phosphorus is going to be placed in the center. We attach the hydrogens back to the central atom, and to do that we used 2, 4, 6 electrons, leaving us a remainder of 2. Now those extra 2 electrons will not get placed on the outermost electron or the outermost hydrogen atoms because they are already satisfied their octet but by becoming helium. So remember, hydrogen only get 2 electrons. So the remaining 2 get placed on the phosphorus itself, the central atom. So here we have a central atom of phosphorus with 3 bonded hydrogens and 1 lone pair. There's 4 domains. 1, 2, 3, 4. Of the 4 domains, 3 are bonded and 1 is not bonded. So on our Vesper chart, we come and we find 4 electron domains, 3 of which are bonded and 1 is non-bonded. It's called a trigonal pyramid. The domain, of course, is still tetrahedral. There's 4 domains. An example is pH3. With 4 domains, sp3 is our 4 fingers, sp1, p2, p3 for 4 domains, and the bond angle is, well, it'll be a little less than 109.5 because of the lone pair pushing those hydrogens enter. So let's draw it. Phosphorus in the center, and again, think about trying your best to draw what this is here in terms of, that's the wrong one. In terms of the geometry, we're trying to draw a trigonal pyramidal. So we have this lone pair of electrons and 3 kind of pointing down. So we'll draw 1 lone pair. Point down is a hydrogen. Point down is the hydrogen. Point down is the hydrogen. And we can see that the bond angle here, if I wanted to label and just keep the red here, would be just slightly less than 109.5. Simply because those lone pair of electrons, remember this highly electron cloud region there is pushing those hydrogens closer together. So the electron domain here of 4, 3, 0, 4 domains, 3 of them bonded, 1 of them unbonded, 3 and 1 equals 4, gives us a molecular geometry of trigonal pyramidal. With 4 domains, it is a tetrahedral, 1, 2, 3, 4 electron domain. This molecule is polar. The area up here would be partially negative, and each of those hydrogens would remain partially positive. The electron density is getting pulled toward the top of the phosphorus. The bond angles we said would be slightly less than 109.5, and it has sp3 hybridization. Let's consider number 4, which is arsenic pentafluoride, ASF5. We'll go to scrap paper first. Let's tally up how many electrons we get in ASF5. Arsenic, who is AS, lives in group 5, so it will be donating 5 electrons to the molecule. And fluorine lives in group 7, and there's 5 of them there. So here we have 35 electrons for a total of 40 electrons by the time we're done creating our molecule. Arsenic gets placed in the center. It's the one we have just one of. It's the least electronegative, and we have to attach back all of the other atoms to the central atom. And notice there's 5 of them, so this means we have to expand the octet. We're going to have a rule breaker here. It's going to have more than 8 electrons around the center. So just kind of roughly putting them here, I'll have 1, 2, 3, 4, 5 fluorines attaching back to the central atom. 2, 4, 6, 8, 10 electrons were used, leaving us a remainder of 30 electrons. Then the rules say, with those 30 electrons, fill the octet of all of the outermost electrons, which are the fluorines. So we'll need to place 6 electrons around each of those fluorines to satisfy its octet. How many did we use? Well, we placed 6 around each of those 5, so we used 30 electrons, giving us a remainder of 0. We've actually just created a molecule that has formal charge, all of 0. Arsenic, who lives in group 5A, even if we expanded its octet, it has 5 valence electrons assigned to it, lives in group 5A, the formal charge is a 0. And each of these fluorines, who live in group 7, also are assigned 7 electrons, have a formal charge of 0. This is the ideal structure, eliminating any formal charge by expanding the octet of arsenic pentafluoride. So we had 5 domains, all 5 were bonded, 0 were unbonded. On the Vesper chart, we need to find the 5, 5, 0. 5 total domains, all 5 were bonded, 0 were unbonded. It's now going to have a molecular shape of trigonal bipyramidal, which is also the electron geometry, trigonal bipyramidal. And there's our molecule AsF5. There's 5 domains, so S, P1, P2, P3, D1. There are only 3 p sublevels, right? 3 orbitals in the p, so S, P, D1 are the 5 domains, sp3d. And when you build this, it will literally have 2 different types of bond angles involved. You'll see that here is an equilateral triangle going around the central atom. Can you see that triangle there? These are 120 degrees around that equatorial position there. This is like the equator. And these axial positions come up and come down. They're like the flagpole positions, straight up, straight down. So you see the 90 degrees or 180 degrees from top to bottom. 90 degrees here. And when you build this, you will see that it literally has 2 different angles. So let's transfer that, and knowing that we have to do our best to actually draw this structure for AsF5. Arsenic goes in the center. One of the fluorines straight up, one of the fluorines straight down. Then we have to build an equilateral triangle around the equatorial positions. So that's how I'll do that. We have a bond angle here of 90 degrees, but between all of those around the center arsenic going around in this circle, these are all 120. So those are all 120 degrees. Alrighty. We said that there were 5 domains, all 5 bonded, 0 unbonded. The name of this is called trigonal, and that's because this is an equilateral triangle. 1, 2, 3, the face of an equilateral triangle. And then the other word is bipyramid, or bipyramidal. Electron domain geometry is the same because all of the atoms are bonded back to the central, no lone electrons. This is a nonpolar molecule, completely symmetrical. 2 different bond angles we have drawn in, 90 and 120, and an sp3d1 hybridization. And one last compound we're being asked to draw, SeCl6, selenium hexachloride, SeCl6. And again, I'm trying to select some from each part of the Vesper chart. SeCl6. So some scrap paper. Let's figure this out. Selenium, find my periodic table, selenium lives here in group 6. So it has 6 valence electrons. And we're attaching back to that chlorine, which has 7 valence electrons. The least electronegative, the one that we have just one of, will be selenium. It will serve as our central atom, and we need to attach all those chlorines back. So you can see we're going to expand the octet in our last example as well, pulling from a 6 domain. So we said selenium with 6 electrons, chlorine who has 7 electrons, but there's 6 of them there, so that's 42 electrons that chlorine will, each of those will donate. Total number of dots we have to place are 48 electrons. Attach all of those chlorines using a single bond and subtract what we've just used. 2, 4, 6, 8, 10, 12, leaving us with 36 electrons to place. With those, our job next is to fill the octet of all of the outer electrons. So each of those chlorines will need 6 dots placed around it. And when we do that, how many did we use? Well, each of those 6 had 6 dots, so we used all 36, so there's none left to place on the central atom. If there are remaining dots, that's where they go next, is on the central atom. So this is our rough draft. We have 6 electron domains. All 6 are bonded, none are unbonded. With the Vesper chart, we need to find the 6 domains, all 6 bonded, none are unbonded. It's going to look like an octahedral structure, both for electrons and the molecular shape. 6 domains says S, P1, P2, P3, D1, D2 gives us 6 domains, and it will literally look like 90 degrees. So I've tried to draw a rough draft there. Let's transfer it. You'll have a chlorine straight up, straight down, and then literally a box around the central equatorial positions. These are known as the axial positions around the center of the equatorial positions. Place all those dots around there. My goodness, I forgot up here too. That would lose me points. Got a lot of dots to fill in, and I'll do so quickly. Please make sure you did the same. Same thing for the chlorine. I have to have the same number of dots as we were instructed to place based on counting valence electrons. There we go. And each direction, it doesn't matter where, they're always 90 degrees. Any between there, you'll find that they're 90 degrees. So we had 6 domains, all 6 were bonded, 0 unbonded. It was called an octahedral. Same because we had no unbonded pair, making this nonpolar. And sp3d2 hybridization, sp3d2. Now I selected one from each position. You're going to be building 20 electron structures, and I bet you'll have a variety of different electron domains and molecular geometries. This is the pattern that we'll follow for all 20 structures. The other part of the directions say as you're building these, this would be like a pH 3, here is your carbon dioxide. As you're actually building these from your molecular models, you're instructed to have your instructor, your lab instructor or the lab aide, check these before you disassemble them. We want to be sure that you're actually seeing the structures and not just putting them on two-dimensional paper. So every time you build a few, call us over and we'll check them off before you tear them back down. Great, I look forward to seeing you in lab.